This is Katie Bowman's AP Problem 2. Let's start off by reading the question. A 0.150 gram sample of solid lead 2 nitrate is added to 125 milliliters of 0.1 molar sodium iodide solution. Assume no change in the volume of the solution. The chemical reaction that takes place is represented by the following equation, and they give us a complete balanced equation here. So, part A asks, list an appropriate observation that provides evidence of a chemical reaction between two compounds. So for part A, I wrote, a chemical reaction occurs because a precipitate forms in the product. The precipitate that forms is PBI squared. Alright, so now part B asks us, calculate the number of moles in each reactant. Okay, so let's move on to part, whoops, my bad, wrong order. Alright, part B right here. So, we're going to start off by taking the 0.150 grams of PbNO32 that they give us in the question. We're going to convert it into moles. So we find the molar mass of PbNO32, which is 331.22 grams. We're going to put 1 mole on top so that we convert it, and that is going to give us 4.53 times 10 to the negative 4 moles of PbNO32. Now we're going to convert NaI into moles. So what we're going to do is we're going to multiply the molarity that it gives us multiplied by the milliliters that it gives us. So we're going to multiply together, and we're going to divide by 1,000 so that when we multiply these two together, we don't end up with millimoles, but we end up with moles instead. So we multiply these together, divide by 1,000, that gives us 0.0125 moles of NaI. Alright, let's move on to part C. There we go, which asks us, identify the limiting reactant, show calculations to support your identification. Alright, so we start out here with part C. So we're going to use the moles that we just found in part B for this part. So we'll start with NaI. We're going to take 0.0125 moles of NaI, and we're going to convert it into moles of PbI2. So the mole to mole ratio is 2 moles of Na, or it's 2 to 1. So we're going to put 2 moles of NaI below 1 mole of PbI2, and that is going to give us 0.00625 moles of PbI squared. We know that this is a 2 to 1 mole ratio because when we look at the equation that it gave us here, there's 2 Ni's right here, but there's only 1 PbI squared when you balance the equation. Alright, so now we are going to look at this one, PbNO32. We're going to turn it into PbI2. So what we're going to do is we're going to take 4.53 times 10 to the 4 moles of PbNO32. It's a 1-to-1 ratio with the equation, so it's going to be 1 mole on the bottom, 1 mole on top. We convert it into PbI2, and that gives us 0.000453 moles of PbI2. When we look at our two answers, this one is a smaller number, so it's going to run out first in the reaction, so it ends up being our limiting reactant. Alright, so now let's look at part D, which asks us, calculate the molar concentration of NO3- in the mixture after the reaction is complete. So after the reaction is complete, NO3 ends up over here in an aqueous compound. There is a coefficient of 2 in front, which when we find the concentration, which is the same thing as molarity, we're going to do moles over liters, and we have to multiply it by 2, because like I said, there was a coefficient of 2 in front of the NaNO3. So we're going to do 2 times 4.53 times 10 to the negative 4 moles, which we found in part B, and we're going to divide it by the millimeters that it gives us in the equation. I converted it into liters so that the units are consistent, and that became 1.25 liters, and that gives us 7.25 times 10 to the negative 4 molarity for part D. So now moving on to part E, which asks us, circle the diagram below that best represents the results after the mixture reacts as completely as possible. Explain the reasoning used in making your choice. So I chose this one right here, and I chose it because in the reaction, the solid that forms is PbI2. You can see that right there. It has an S next to it, which means solid. So the liquid that is left, or the solution that's left in the beaker that's here, would be NO3 or NaNO3. And since the charges in NaNO3 cancel each other out, we know that there would be an equal amount of them in the solution that's left, in the stuff that didn't turn into a precipitate. And when we count 4 NAs, 4 NO3s, and that would be our answer for that. So that's it. Thanks.